Otherwise, we'll move ahead to first law derivation for open systems. Okay. So we have talked about this Joule's experiment, where we see that pedal wheel is doing some work and that is raising the temperature of that water, and then we saw that after cooling that you can get back to the initial conditions and how we complete a cycle. Okay, so this is how we defined the Joule's equivalent or mechanical equivalent of heat. So this was the first experiment which has shown that heat and work are equivalent. Okay, so this we discussed. Then we defined the SI units for Joule, and if you have work and heat both in SI units, then J becomes 1. And we talked about energy of a system, what is contained, and it is a system property. Then we talked about what are the various forms. We look at this again. So basically, for closed system, we neglected these terms. Okay, closed system did not have any kinetic and potential energy. That was the assumption. Now we go to open systems where we have fluid moving. So there we need to consider at least kinetic energy. We should consider, and since it is moving, to keep it more general, we'll derive equations for potential energy also. We'll keep that term also. Okay, so we'll see moving forward. So these are the different ways in which we can write the first law. And then we talked about specific heat at constant volume, enthalpy, Cp. Any questions till now? Please ask me. Otherwise, we'll move to open systems. Okay, I'm assuming that everyone is clear with these topics because these are the building blocks of your first law. Okay, we talked about enthalpy heat, PMM1, a solidity system, and how do we have shown using an example that how first law can be applied to a closed system. We took some numbers and we see how these numbers are distributed. So let us now come to open systems. So for open systems, we looked into what do we mean by steady and unsteady processes. Then we took a simple example of water filling in a tank, and from that we derived the equation for conservation of mass. Okay, we took simple examples of a flow having one inlet and one outlet. If you have multiple inlet and outlets, you just sum over them. Then okay, one thing we forgot yesterday, we'll continue with that. So no questions till now. Should we move ahead? Fine. Moving on. Yes, any questions there? Okay. So moving on, what we have seen in previous slides, previous lectures actually, that in a flow field there is a difference between pressure upstream and downstream locations. Okay, so there is a delta P. So because of that, there is some work involved. You need to push the fluid into a domain, and then when it goes out, then also it does work. Okay, now let us see how that happens. So let's take a simple general example. Let's say this is my system. This is an open system. Fluid is entering from this side and fluid is leaving from here. So let's say dm1 is the mass entering per unit time. So for example, in 1 second, dm1 is the mass which is entering this domain. And we have pressure and area of this opening is A1 and P1 is the pressure here. Okay, at the boundary. And similarly, when you talk about the exit, we say that dm2 mass is leaving per second, and P2 and A2 are the pressures and area respectively. So if dm1 and dm2 are different, so is a steady or unsteady system?
Unsteady.
Unsteady.
Yeah, so if you want to keep it steady, then we will have both the masses to be equal. Okay, now let's see how we define or how we derive work done or flow work. Okay, so let us imagine that there's an imaginary piston here, okay, which is shown in haste. So in time t or per unit time, it moves a distance dx and it pushes this much gas inside this. Okay, let us say that gas volume is dv1. Now it is acting against some pressure. What is that pressure? P1. This fluid is being pushed against this pressure P1. So what will be the work that is involved? dW is the flow work. It means it is happening at the inlet. So for inlet flow, work done will be PA is the force into dx. This is work done. Now from here, can I write A1 into dx is dV1, area multiplied by the length will give you the volume. Is it correct?
Yes, sir.
Yes, sir.
Fine. Now I know that dV1 is equal to, this is intensive into mass. What mass is entering? So can I write it like this? dW flow is P1 V1 into dm1. Okay. And if we write in intensive terms per unit mass basis, then I will say dW of flow is P1 V1. So this is for inlet. Similarly for outlet we can write dW flow is P2 V2. Now for inlet, work is being done on the system. Something is getting pushed inside the system. For outlet, flow is done by the system. The gases push here the pressure is P2, so the gases push against it and they move out. So the work done is by the system, and in general we can say that dW flow is P into V. Okay, so this is something that we need to consider when we derive energy balance for open system. So flow work is also we need to include. Okay, another point I wanted to discuss today is about energy. So as I mentioned that these two terms we neglected in previous analysis. In closed system, these are not required. But now kinetic energy and potential energy will be, we are required to consider, because the fluid is moving, it has some kinetic energy is definitely there. It could also have potential energy based on the height. Okay. And in general for open system we considered only internal energy U. Okay, so for kinetic energy we will take half mv square, mg is h or mg is z, and U that we are considering till now, that was only molecular energy which contains translational kinetic energy, rotational, vibration, etc. So this is all molecular. So this is also kinetic energy term, and U also contains kinetic energy. So can anyone tell me what is the difference between these two?
One is microscopic and other is macroscopic.
Yes, correct. So this kinetic energy, when I'm talking about the kinetic energy that is contained with the molecules which are moving randomly. Okay. So if you look at this motion, on a whole, the molecule are not moving at the system is not moving. The system is stationary, but molecules are moving on the microscopic level. But this kinetic energy is when the system is also moving. For example, when you have a flowing liquid has some velocity, so that we need to consider. Okay, so these terms will also get added in energy equation, which we are going to derive now. And we can write this in per unit mass basics or intensive terms. So we'll say E is equal to U plus half V square plus GZ. Okay. Now moving on, we'll now talk about conservation of energy or energy balance. So I preferred this term because we are talking about conservation of energy. We are looking into what is the total amount of energy that is being supplied to the system, how much the system is doing work. So overall, we are writing a equation for conservation of energy. Okay. So let us begin with a very general system. Let us say that we have a system shaped like this, which has multiple inlets and multiple outlets, and these are the mass flow rates. And that one is the rate of mass flow per unit time. Okay. Now we need to consider energy. So let's say the fluid which is coming in the first inlet, which is going coming at the rate of m dot 1, it has energy which is E1. Similarly, m dot 2 has energy E2. Okay, E is what we have discussed in this slide. So someone was asking last class. So for again, I will repeat, for closed system, we were talking in terms of U only because other terms are negligible. Now we need to talk terms of E. Okay, so that is what we see here. E is the energy of the incoming fluid, and similarly, this is what is leaving the system. Okay, so like we derived for mass, we said that how the mass of the control volume is changing with time, d by dt of that is equal to sum of all mass flow inlet minus outlet. So what is coming in and going out, that is what we call as balance or conservation. So similarly we discussed, can we use energy balance in the same form? Yes, we can do that, but we need to take care of heat transfer and work. Okay, that what we have discussed in our previous slides. So let us see how that is done. So let us take a simple system. Let's say that it has only one mass inlet and one outlet. We can have multiple also, but let us begin with a simple system and then we'll generalize what we have derived. Okay. Now let us also say that pressure here at the inlet is P1 with E1 energy and V1 is the velocity. Okay, so when we talk about velocity, I will keep it bold, and when we talk about volume, it will be right. So generally we'll talk about intensive volume, which will be small v. Okay, specific volume. This is for velocity, so don't get confused. Any questions, just feel free to ask. Similarly, now M2 will also be leaving. Let us to keep it general, we'll say that M1 and M2 are different. That can later be made equal for if you have a steady case. Okay, so it has P2 is the pressure, V2 is the velocity of the fluid stream that is leaving, and E2 is the energy that it contains. Okay, so we can write P in or P1, whatever you are comfortable with. Now we'll also need to consider heat transfer. So we say QCV is the heat that is getting transferred to this control volume. Okay, that is being supplied to control volume. And Wx is, let's say, the shaft work which is getting done. So this is the output. The system is doing work on some shaft or any other, by any other means. This is what is getting out. We are getting out from the system. Okay. So this will increase your internal energy or total energy, and this will decrease. And plus the flow work. So let's see. So this equation. So first let us talk about this. So we are again talking about how the total energy content within a control volume changes with time. Okay. So for another interesting point, for open systems, okay, we talk about rates. Generally, we talk when we were in closed system, we're talking about energy only. Now, since the fluid is flowing, so we generally talk about rate because it is related to the flow rate of fluid. Okay, so you say how the energy within the control volume is changing with time. Okay, d by dt of ECV, which is equal to the rate of flow of energy inside in the inlet plus. Okay, so QCV also has a dot here, which is actually I missed from here. Let me just correct it. So QCV is not only the heat, it is the rate at which heat is supplied. Okay, and WCV or WX will also be the rate at which work is done. Work done per unit time, which is actually power. Why should I write in that terms? To make it consistent. Because this is per unit time, so this also has to be per unit time. Okay. So basically we are talking about how much energy is entering the system per unit time at the inlet, how much is leaving. So that one we are subtracting. And QCV is added to the system, so it is positive. W is being done by the system, so that's why it is negative. Is this clear to everyone?
Sir, where the work is done in which thing?
Let us say that, okay, we are not talking about a general system. Let us say that some shaft is there. Okay, it has some blades. So generally, after deriving this equation, we'll see how it applies to different objects. So let us say it is a turbine. Some work is getting delivered to these blades. The blades are rotating. That can be done,
Yes, sir.
but we will come to that. For now, let us just assume that whatever terms are possible, we'll consider that and we'll derive a very general equation. Okay. Later we can remove some terms. If there is no work, we'll remove that. Okay, moving on. So now we'll try to expand these terms. So E dot inlet I can write as M dot 1 into E1. Okay, similarly E outlet is M dot 2 into E2. Okay, rest of the terms are same. Now what we have discussed previously, WCV. This is again W dot CV. Okay, rate of work done is equal to W dot X. So let us keep this term X for general work. Let us say shaft work. And what is this? Can anyone say what this term will stand for?
Flow work.
Flow work.
So this is what I mentioned that we need to consider. So we'll talk about work done on any external body, work done by the system, plus flow work is anywhere there. So that again we need to subtract. So P1 is what is work is done to the system. So it is minus, because the general convention that we agreed to is that work done by the system is positive, work done on the system is negative. So this is the work done by the system, that's why it is positive. This is work done on the system, that's why it's negative. And this is again following the same convention, work done on a turbine or let us say shaft work. A very general term is shaft work. Okay. So now we'll substitute this WCV in the previous equation. So just take this and substitute it here. So what we'll get? These terms were already there in this equation, and then up to here is the same. Okay, let me use a pen. So up to here is same what we have derived. From here, we have just simply substituted these terms instead of W dot CV. Any questions on this? We're doing simple algebraic manipulation, that's all. Everyone is fine? Okay. Moving on. So I would again request that be very attentive, look at what are the terms involved, and it is a little long derivation. So feel free to ask me if you have any questions. And I will also upload these slides so you can look at it again. And the next class, if you have any questions, just ask, because this is a very basic equation what we are deriving. This is we'll go to general energy equation and steady flow energy equation, which will use these equations to solve many numericals. So I want you to be very clear with all the terms which are involved here. Okay. So moving on. Now we have just substituted WCV in this equation for energy balance. Now what we can do is we can do some rearrangement. Okay. So you see the terms marked in red. What is common between them is, can anyone say?
M1 dot.
M1 dot.
Yeah. So M1 dot is common between the red terms and m2 dot is common between green terms. So the same equation I did some rearrangement to make some modifications. So what I can do is I can take m1 dot as common and make one term, and I can take m2 dot common and make another term like this. So m1 dot I took common and I have added p1 v1 plus e1. So this is the first bracket. Second bracket will be E2 is what is leaving the system. It is exiting the system. So that again goes to minus. So m2 dot p2 v2 plus e2. So this is the second bracket, and as usual we have q and w. Okay. So just some rearrangement, and other terms are retained the same. Now this is what we have in the last slide, right? Now we know that we'll expand. E1 is U plus, as we discussed in the last slides, right? Internal energy plus kinetic energy plus potential energy. This is the total energy contained in a flowing stream. Okay. Now we'll just substitute this in this equation. So instead of E1, I now have this term within this curly bracket. U1 plus half V1 square plus GZ1, and the rest of the terms are same. Okay, as you can see from here. Similarly for E2, E2 we replace with this. So we have what are the terms within this curly bracket plus other terms which we have in the previous equation. I hope this is fine to everyone. Okay. Now we also know that H on enthalpy is equal to PV plus U, right? So what we see here is that we have PV plus U. Okay, similarly we have PV plus U in M2 also. So what we can do is we can replace this by H. Okay, so what the equation will become? So instead of this I have H. So left hand side is anyway the same. Right hand side we have m1 into m1 dot into, instead of this I have h1 plus these terms are same what we have previously, minus m2 dot. Now instead of this we have h2 plus rest of the terms are same plus work done, short work done basically. Fine. So can I write it like in this form? So what I did was I just take some rearrangement. I take Q and W separately. So I can say d by dt of ECV is these terms, because Q is increasing E, W is decreasing V, plus m dot into whatever the energy is contained in the incoming fluid, minus m dot into whatever energy is getting pushed out or moving out with the moving fluid. Is this clear to everyone? Any questions on this? Fine. Let us move on. So this is the equation what we have derived in the last slide. So this is a general form for energy balance, or we can also write. So this what we derived is for one inlet and one outlet. Okay, you can write M1, M2, you can write M in or M out, ME. So whatever like is convenient, that can be used, but this is the form of equation that we will be following. Okay. Now to keep it general, what we can do is instead of one, we have multiple inlets and outlets. In that case, I will do a summation over all the inlets, summation over all the exits. So exit is denoted by E, inlet is denoted by I. Okay, the terms will be the same. So this is our general form of energy balance or conservation of energy. Any questions so far? Is everyone clear what we did here?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, fine. So this is important equation that we'll keep on using in lot of numericals. Okay. So now let us look at what happens in a steady state. So what we have derived is a general equation which can be used for any scenario. Let us take a particular case of steady state. So what will change? D by dt CV, what it will be? Will it be 0?
Yes, sir.
Yes,
Okay.
sir.
So this will be 0 because it is not changing with time. Then we can equate these terms. We can say that also to this m1 dot will be equal to m dot 2 because mass of the control volume is not changing. MCV is constant with time. So this has to be same. Okay. So using this, what we can write is we can take this term. Let me use a pen. So we can take this term plus QV is equal to, let us take this negative terms to the other side. We draw it here. So is equal to this plus work. Okay. So this is basically input and m dot m2 gets cancelled. So we are taking these terms h1 plus half v1 square plus gz1 plus q is equal to h2, these terms from here, this term from here plus ws. This is the shaft work. Okay, so this is what we call as steady flow energy equation. Okay, so this is one of the most commonly used form of energy balance equation. Any questions on this? Or everyone is clear? Okay, then let us try to apply this equation at different scenarios. Okay, so let us talk about turbine. So someone was asking how we do work. So basically turbine will have a shaft, okay, and will have blades mounted on this shaft. So as the fluid flows through the turbine, it also does work. Okay, it is rotating this shaft. So because of that, work is being done on that turbine. Okay, so we'll start with the general form of the equation. Now basically when we use this equation, what we need to do is we need to look at what terms are important, what terms we need to retain, and what terms we'll remove. Okay, so this is my system. We are getting some work output from that. We can call it Wx or simply W. And Q is the heat supplied. Okay. It could be heat loss also, but we'll keep in that term. If it is heat loss, then it will be negative. That's all. And this is the inlet. This is the exit. So this is what we start with, the general form of energy equation, what we have derived in the last slide. Okay. Now what it says is that will neglect kinetic energy and potential energy terms. Okay, sorry, this will get cancelled. Is that this will be equal to this. This is not like very, if you want to keep it accurate, you can retain it, but generally these terms are negligible. The velocity is not very different, so that can be done. Okay, and similarly, this height is also not very different, so that gets cancelled. So what we're left with? We're left with Q plus HI is equal to W plus HE. HE plus W. This is what is remaining. Or I can write. So basically, if I have a system like this, what I am interested in, I am giving these are the properties which is given. Q is given. The target or objective of most of the equations that we'll see maybe is to obtain what is the work done by that particular turbine. So to obtain work done, we can rearrange this and we can express work done in this form. Okay, and this is generally expressed in kilojoules per kilogram. Okay, Or I can write in, if you multiply it with mass, we can write W dot of Cv is equal to Q dot of Cv plus, now the mass term will come, delta H. Okay, so this is how you apply this steady flow energy equation in on a turbine. Similarly, in a similar way, you can do it for a compressor also. We'll see. Any questions on this? How this was done?
No, sir.
Okay. So one thing I just wanted to repeat. So in some examples, you see that we neglect kinetic energy, kinetic and potential energy terms. So in general, this is it is quite accurate to neglect this, because generally the inlet and exits are at the same height, or there's not much difference in height, especially when you're talking about gaseous flow. So that won't cause much of a difference. But for some examples, we'll also say that inlet velocity is equal to exit velocity, which may or may not be true. So then you have to look at numerical, that how different are they, or whether you want to neglect this term or not. Okay, so generally, if you have the same velocity at, let us say, a pipe flow, then it could be a reasonable good approximation. But if there's a large difference in area, okay, so you see that the area difference is there. It is smaller, this is more. So if this difference is large, then it is better to retain this kinetic energy terms. Otherwise, you can neglect and you can calculate work using this. In general, this is true, but just be a little bit careful. Fine. Now let's look
Sir,
at yes.
sir, this is an example of control volume system.
Yes.
Okay, sir.
So this is an open system. Okay. So let me. So basically, what happens is that this is your turbine. Okay. Let me draw it again. So this is your system. Okay. Then this diagram is a little confusing. So this is your control volume. What is coming inside is your control volume. Now you have fluid entering this. Okay. This is your inlet stream and this is your exit stream. So what we have discussed in previous slides, but we have a box, right? Yeah. So we talked about the box. So now imagine that instead of box, you have a turbine. That's it. And all the equations are remaining the same. This is your inlet, this is your exit. Is it clear now?
Yes, sir.
Moving on, let us go to turbine. Now we'll talk about compressor. So turbine is basically, we talk about positive work because we obtain work. Work is done by the system. Okay, the moving fluid is doing work on these blades, and which is external. So it is doing work on something else. Now that shaft is actually doing work. Okay, this has not come correctly. So this is the, I will just change these figures and put that in your. So this is the inlet, this is the exit. Okay, this is the heat supplied and work done. Anyway, so this will again have a shaft and blades will be mounted on this shaft. Okay, next class I will show you some actual images how this turbine or pump look like. So what will happen is that fluid is moving through there. Now these shafts are rotating, and that is what is doing work on that fluid. So that's why we call negative work. Work is done on the system. Okay, so this should be, actually this is what we have. So basically we can put minus W. Okay, so now this is the steady flow energy equation what we have derived. For this particular case, we'll say that again we'll assume that kinetic and potential energy changes are negligible. So similarly we can say that work done by the control volume is whatever the heat supplied plus n dot into delta H. So for turbines and compressor, what we'll see is mostly delta H term is the important. That is what will determine how much work can be extracted from that system. Okay, we'll see. Okay, so what I will suggest you is that once I upload those slides, you can go through the whole derivation once. It is a little involved derivation, and you can see how this energy balance is applied to these devices. Okay, turbines and compressor, and then we can when we go to numerical examples, then it will be more clear. Then you see how these terms are, what are the typical values for enthalpies, and how these terms are getting used in any numerical, and how do we find out, let's say, work, what is the work done, or heat transfer done by the system. Okay, so this I would stop it. So I would stop for today.